Hello everyone and welcome back. Now in this video we're going to continue our exploration of dictionary-based methods for identifying nonlinear dynamics. And in particular what I would like to do in this video is use dictionary-based methods, so SINDy type arguments, to discover conserved quantities, right? So conserved quantities appear all throughout dynamical systems, primarily coming up from problems in physics, places where one might have maybe conserved energy or conserved momentum. But of course, in some dynamical systems, there are conserved quantities we didn't even know they were there. And so what we would like to be able to do is identify if they are actually in the problem. Now let's start out by discussing what actually is a conserved quantity from a conceptual dynamical systems level. Well, if we start with a dynamical system, let's look at a continuous time dynamical system, for example. The same thing can be done in discrete time as well, but for today we're going to work with continuous time. Then a conserved quantity, so if we assume that x is in, say, Rd, a conserved quantity is a function from the state space into the real numbers that is constant along trajectories. So that is c of x of t is equal to c of x of 0 for all t. Right? And so, of course, we're making the assumption that all t that this solutions exist along, but this is going to hold for every single solution, right? So this is what it means to be conserved. It means the output of the function c is the same along every single trajectory. Now, we can actually differentiate this identity to get a nice characterization of our conserved quantity. So if we differentiate both sides of this, this is a constant. Here we can use the chain rule, and in fact, we would get this identity that the gradient, so the derivative of this scalar valued function c, dotted with the right-hand side of the dynamical system, that's just the time derivative here, is equal to 0. And in fact, you want this to hold for every x in the phase space. So I'm going to sort of wedge this in here. I know it's not the most beautiful notation, but this is really a characterization of a conserved quantity. Now, if you want to think about this on a conceptual level in terms of calculus, right? So first of all, we know that the gradient of a function is perpendicular or orthogonal to its level sets. We see from this term right here that solutions lie along the level sets of the function. And this tells us that the flow of the dynamical system, the tangent to the flow, is orthogonal to what is orthogonal to the level set. So sort of double orthogonality. It tells us that solutions move along these level sets. Now, this is just a characterization of what a conserved quantity must satisfy. But the problem is here, this still doesn't tell us how to actually find this function c. And so as I mentioned, what I would like to do is I would like to try and at least approximate it from maybe data gathered from my dynamical system. And I'm going to do that by defining a dictionary again. So here we are, very similar to what we did with SINDy or EDMD, all of our sort of favorite methods that we've learned so far. I'm going to come up with a dictionary of functions that are all functions similar to C from the state space into R. And so if I just write this, little k goes from Rd into R. And what I would like to try and do is I can expand. So let's do this. Expand. I'm going to assume that C lies in the span of this, just like we did with SINDy, right? But we're going to say C of x is equal to some unknown coefficient. I'll call it psi of theta 1 of x plus psi 2 of theta 2 of x plus psi capital K of theta capital K of x. All right? And so, of course, the name of the game is to identify the psi's that make this thing a conserved quantity. But you have to be careful here, right? This is just an expansion. We need to actually build in, something that's going to make this a conserved quantity. We are going to use this equation right here. So how are we going to do that? Well, we are going to, so we want these, I'm going to use capital psi to be the vector of all of these psi's. This is a vector in R capital K. We want to identify this so that, well, so that what? So that this identity holds, okay? So that means that 0, and then if I assume C takes this form right here, then differentiating it or taking a gradient of it means that I'm searching for psi 1, that's still just a constant. The gradient of the dictionary element theta 1, again, I can compute that because I got to choose the dictionary element. And then dotted with the right-hand side of the ODE, plus, and then doing this for every single term. Again, I can compute all of these gradients. I define the dictionary. And one thing that we can see here is that this relies on the right-hand side of the differential equation. Now, this method can be applied in two different ways, okay? One way is if you know the differential equation, then you know what f of x is, and you can do all these evaluations, or you can do all these multiplications yourself. But another way is if you don't know the dynamical system and you only have data, okay? So let's take a look at what would happen if we collect data here. So maybe let's do this. Let's say we have data, and I'm going to call that data x capital 1. It's snapshot data, just like we've seen in pretty much every application so far. All right, so this is snapshot data from the state space. And in particular, I'm also going to assume that I have derivative data. So again, this is kind of like the SINDy method, where I can take approximations of the derivatives here. I'm going to call that derivative data x1 dot all the way to xn dot, okay? Now, the important piece of having this derivative data is that this is an approximation of f at your data points, right? So this is, this should be a good approximation of f of x1 and then all the way up to f of xn. So even if you don't know the dynamical system explicitly, you still have an approximation of its right-hand side, assuming you can get a good approximation of these derivatives. And essentially, solving this thing right here, if you plug in each of the data points, you get a linear algebra problem, just like we had before, right? So let's just say this, linear algebra problem. Okay, let's take a look at what this looks like. I'm going to write it like this. I'm going to call it gamma, and it's going to be gamma of capital X comma capital X dot. The only reason I put these in here is to emphasize it depends on the data and its derivative times this unknown here, vector, and it's going to be equal to 0. So it's a null space problem. The question is, what is this gamma matrix? Well, this is where gamma of x comma x dot, it's just going to be all of these evaluations right in here. So let's take a look at this. This will be the gradient of theta 1 at x1 dotted with x1 dot. That is this term at the first data point. And you can go all the way down the columns here and do this for every single data point. So you do the gradient of theta 1 at capital Xn dotted with Xn dot. And okay, so it's going to be a big ugly matrix. Then across the rows are going to be the dictionary elements. So here we go. Theta k Xn dotted with Xn dot. All right, so it's a big ugly matrix. In fact, this matrix, is in our n by k, and you should have that n is much larger than k. You should have more data than you have unknowns for your system. And so, of course, one way you can try to solve this is by finding, you essentially just want to solve this null space problem. One way that you can do this is you can use the SVD. And the reason I want to do that is because if I take the SVD of this matrix, right? So we've seen this a million times now in this course. It's really sort of one of the most powerful things that we can use. Since n is going to be larger than k, this is the rank of this thing could be maximally k. So this is going to have some zero singular values. Then we can use the vectors of this, the vectors corresponding to those zero singular values in the matrix V to get a basis expansion for the null space. Again, go back to our lecture on the SVD. We talked about this a little bit. So that means that we look for the singular values in the SVD, and we use the ones that are close to zero, because of course this is data. It's going to be approximately close to zero. And then we're going to use the corresponding vectors V to those singular values to form an orthogonal basis of the null space. That means that through this method, we're not only potentially finding one conserved quantity, but we could find multiple conserved quantities if there are multiple singular values close to zero or at zero numerically for us here. Okay, let's take a look at an example. We're going to work with a very simple, at least looking, three-dimensional ordinary differential equation written in the variables x1, x2, and x3. So here's our ODE. As I know, actually, this ODE has two conserved quantities. This is momentum, and this is the energy. Now, if we think about this in terms of conserved quantities, what does this tell us about the system? Well, we know that each conserved quantity conserves or forces the flow of the dynamical system to be on the level sets of that conserved quantity. Now, the level sets here are approximately two-dimensional. The level sets here are approximately two-dimensional. And the trajectories have to lie on intersections of these things, which two dimensions intersecting here is a one-dimensional set. So effectively, the solutions to this differential equation are uniquely determined by the intersection of the level sets between these two conserved quantities right here, okay? This is an integrable system. That's essentially what it means. It means that there's so many conserved quantities that the only way the solutions can exist is if they are on the intersection of these things, the little one-dimensional intersections. But here's how we're going to do this with the data-driven framework, okay? So here's what I'll do. I'm going to gather up some data from my system. So I'm going to do this for 20 initial conditions with random initial conditions, and I'm going to do this for my conservative ODE, which is what I've called this thing right here. Now, because I know the right-hand side, I'm not going to use derivative estimates. I'm actually just going to use the right-hand side to get the x dot terms, or I'm going to use f of x here, okay? So, of course, I'm doing a little bit of cheating just for demonstration here. Of course, if you only have data, then you would want to do this in the data framework. And what you're going to see actually is that what's happening here is part of a much larger picture that has to do with the Koopman operator and its eigenfunctions as we progress through this lecture series. But for now, let's just use the right-hand side. and I'm going to create a huge gamma matrix. I'm going to go up to quadratic terms. Again, because I know, I'm kind of cheating here because I know the answer, but I'm just trying to illustrate to you how things work. So let's build up my gamma matrix in terms of the data I have, and using a library up to quadratic terms in the x1, x2, and x3 variables. Now remember, we said that we wanted to use the SVD to check if there should be any conserved quantities here. So here you have it. Here's my nice SVD computation. Let's actually run this, and let's take a look at the SVD spectrum. Now, okay, so the SVD up here, here's the singular values. You can see that there's a lot that are very, very large. Again, the scale of the vertical axis is 10 to the 4. So even though it looks like there's a lot that are small, that's sort of just because of this scale. And in particular, you can see two that are basically sitting at 0, whereas the next smallest one is off of 0. In fact, we can plot this, or we can print this. Let's print the diagonal of S. And so this is 10 to the 4 being multiplied in here. So this is, this is actually much larger than it looks. Multiply that by 10 to the 4. But there it is. There's 2 0 singular values. What does that tell us? There are 2 conserved quantities in the system. Now, we already knew the answer, of course, but this reinforces it. It tells us that the data told us that there's 2 conserved quantities in the system. So let's actually extract out those conserved quantities. And these things are going to be, let's take the last column of V here. So, the second to last column of V. So these are the coefficients in my, these are the coefficients in my expansion. Right? So it's kind of hard to see, but in this case, you can see that there are 3 terms lit up. Similarly, in this case, there are 3 terms lit up. These are sparse vectors, but what I want you to understand is these are sparse orthogonal vectors. They have nothing to do with the original momentum and the energy of this system. And that's because the computer does not care about energy and momentum. We care about it because these are physical quantities that we are interested in as scientists, as mathematicians, maybe as physicists or engineers. But this vector here, I believe this is an x2 squared. This is an x2 cubed, or sorry, x1, x2 term, or something like that. And we can show that the momentum and the energy lie in the span of these 2 things, but all that's been given to us is an orthogonal representation in the coefficient vectors for these conserved quantities, okay? So I want you to really sort of understand what this can give you and what it won't give you. It can give you the existence of conserved quantities. It won't give you it in physical coordinates because the computer doesn't care about physical coordinates. The SVD gives you this sort of orthogonal representation where the orthogonality is in terms of the coefficients in your span of your dictionary elements. Now, just in case you want to see this, if you wanted to plot, this is the plot of one of the level sets of the momentum. In this case, it is the 1/2 level set, so L is equal to 1/2. Of course, you can see this is a sphere. And then plotted along this thing are a bunch of different trajectories to our dynamical system in terms of just these level sets, right? So you can see what's happening here. Each one of these colors represents a different trajectory. It's a one-dimensional curve. Similarly, if you wanted to do the same thing for the ellipsoid that describes the energy here, you get this sort of elongated, sort of egg-looking shape. But again, the trajectories are plotted on top of this thing in each one of these different colors. If you wanted to plot a single trajectory, you would take a level set of this momentum and you would take a level set of this energy and you would look at their intersection, and that one-dimensional intersection would be, one of these curves potentially. So What we've seen in this lecture is how we can use SINDy and dictionary-based methods, really sort of EDMD, in order to discover conserved quantities of our dynamical system. What we're going to come back to in the next lecture is an auxiliary function framework. It is a larger version of what we're seeing here that encompasses a wealth of problems. And as we progress through our understanding of auxiliary functions, we are going to couple it with EDMD to do more than just find conserved quantities, but maybe find Lyapunov functions just from data. So I'll see you all in the next lecture, everybody.